Hi everyone, today we will deal with the line equation. We would like to represent the line using an algebraic representation instead of the geometric figure that we are used to see. But we will actually start with the line represented geometrically as we are used to. Let's say we have this line drawn on the Cartesian system of coordinates, and let's see what are the main characteristics that you have to take notice of in order to represent the line using algebra. So, first of all, I notice 2 points that are special between the line and the system. Those type of points are called the intersection points of the line with the coordinate axis. So this point would correspond to the intersection with the x-axis, whilst this point is the intersection point with the y-axis. But actually, I would like you to notice a more subtle thing that we have to take notice of in order to represent the line algebraically. And this is the slope of the line. The way that it rises in y values between adjacent points, or between any 2 points actually. We can choose any 2 points. For example, I'll choose this point, which has coordinates 1 and 3. And I can choose, let's say, this point. So, to make it clear, this is the first point, and this is the second point that we chose. And the second point has coordinates 3 and 5. And we can find how the y coordinate changes on the line when we move from this point to this point. Okay, we will call it the y difference, the y value difference, or usually it is written as a triangle y or delta y, and it equals the second value of y, y2, which corresponds to the y value of the second point, minus the y value of the first point. Okay? So this is the difference that we get by looking at the difference in height that we represent as we move from the first point to the second point on the line. But in order to find the rate of change on this line, we have to also take notice of the change that we had to take. So we also take the difference in the x values for those 2 points. x2 minus x1. And actually the slope, written as the letter m, is represented as the difference ratio between those 2 parts. But since the rate that we want to represent is the rate of change in the height of the points, meaning the y values change as we move from one point to another, we will actually use the y change as our numerator. And the denominator will be the change, the corresponding change for the x values between those points. So we take the difference ratio and we can expand it as follows. And this is the slope. But actually I can tell that the slope for this line has to be fixed. Why is that? Because the line doesn't change its direction suddenly. It always goes the same way to infinity. Both ways. Here and here. Actually, this line it's not a line per se, it's a segment, a line segment that I draw, just for convenience, in order to analyze the behavior of this section. Because the line is actually homogeneous in its behavior, we can look at a segment and take out from it the general characteristics for the line as a whole. So the slope is a general characteristic for the whole line, and it doesn't change. It has to be a number, a fixed number that represents a specific line. That enables us actually to take some general point on the line and some fixed point on the line. For example, let's choose this point as a fixed point, x1, y1. But now I will not take a fixed point as my second point to which I move as another point on the line. I will take a general point, okay? And this approach will enable me to represent any point on the line using algebraic equations, okay? So let's do the same formulation for the slope of the line, but this time as my endpoint, I will choose a general point. That's why I won't specify an index number for this y, because it's not a specific y. It's any y for a point I might choose on the line. And because I know this difference between any point and some specific point that I fixed on the line, divided by the same x value that has to correspond to this y, of course. It is not some x value that is just by itself. It has to be part of this general point, because a point, we remember, it's always a pair of values, the first value being the x value and the second number being the y value for this specific point. But in this case, we chose a general point, but it doesn't allow us to disconnect the x and the y. They both belong to the same general point. And from this general x value, we subtract the specific x value of the point that we fixed. So now that we have this general point present in our formulation for the slope, we can multiply by the denominator as follows, and we get this equation. Of course, this x minus x1 cancels on the right side, and we are left with y minus y1. And I will just change the order of the two sections of the equations. So we get this. And this thing is actually the basic form for the line in algebraic terms, meaning that we can find any point on the line, and of course we have to determine, before we use this equation, the slope of the line. Without the slope, we won't be able to determine some general point. How can it be useful? Because once we know m, and we know x1 and y1, since we chose it as a specific point that we know lies on the line. Using this equation, we can find at which x, for example, the line will include a point with some height, which corresponds to a y value for that point. Or, conversely, we can, for example, ask, for this height, I want to find the place where the point reaches this height y, specific y that I take. I want to know at which x that happened. Okay, so we can go either way. Using some x that we state, we can find the corresponding y of the point that should be on the line, according to this equation, or using some known height for a point on the line, we can find the place, the position on the x-axis for which x it appears. So this equation is one of the standard ways to represent lines using algebra. We don't have to draw now every single time the coordinate axis, the Cartesian system, we can use just the knowledge of one point existing on the line, the slope of the line, and from that we can determine any point that we want. In essence, we can construct the entire line, a set of points that represent the line. So this equation is one of the very useful and concise ways to represent a line using algebra. Any point on the line that we wish to represent, either finding the x or the y value, stating one of them as a given value. I hope you found this video useful, and next time we will extend our knowledge about algebraic representations. We will check some other alternative ways to represent lines using algebra, and I'll see you next time on our Analytic Geometry online course.